All right, so we're going to go ahead and get into this next section of notes here. So today we're going to be in 11.2, and we were talking about arcs and chords of a circle. So we've talked about arcs already a little bit, and specifically arc length in the last lesson, and now we're just going a little bit more in depth with them and how we can actually find their measures as opposed to their lengths. So first off, today is the 4th, and the objective for today is we want to use this information about chords and arcs to find some different lengths, specifically with chords, and then some different measurements in terms of arcs. So first off, what does that mean if I say a chord? Well, a chord of a circle is just a line inside a circle, that connects two different points. Okay, a chord is just a line inside a circle that connects two different points. So for example here, one thing that we could see if I draw a circle, we have the center right there, and then a chord just connects two pieces or two sides of the circle. So for example, one chord could be like this, where it's just connecting sides of the circle. Notice in the past we're used to seeing that go through the middle, and if it did go through the middle, we would call that the diameter. But in this case, chords don't have to necessarily go through the middle. They can, but really they're just lines inside the circle. Okay, and this is helpful because when this happens, I'll just go ahead and label this. This would be the chord here, and then this piece right here, go ahead and kind of bold that out a little bit. This kind of bolded section there is going to be the measure of an arc. So we talked about arcs last time. We said that's just a portion of the circle, and we talked about how to find their specific lengths using the formula that we talked about that deals with circumference. Now we're talking more about their measurement. So not what is the distance from one point to the other, but instead we're talking about what portion of the circle is that taking up, how many degrees. Okay, and we'll practice that more here in just a minute. Okay, next piece here is what we have, a theorem that kind of goes with this, the congruent arcs theorem. And we can say this, we can say in the same circle, or in congruent circles. Okay, in the same circle or in congruent circles, two arc measures are congruent if and only if, and we're going to see this phrase actually a few different times today. We're going to say those measures are congruent if and only if their chords are also congruent. So the only way that I can see that arcs are going to be congruent is if the chords that are connected to them are congruent as well. Okay, and the if and only if part means it works both ways. So as in the same way that the arcs can only be congruent in that way, the chords can only be congruent if the arcs across from them are congruent as well. So again, for example here, I could draw a circle, and let's say we have two different chords here. And let's say this will be the center. Okay, we'll say these are congruent. These are the same length, whatever they are. It could be 4, it could be 10, it could be any number really. Okay, and then let's say the arc measures here. Let's say the arc measure of this one is, we'll go 120. Let's say it's a third of the circle. It's probably not to scale, but that's okay. Okay, it's saying if this is the case, 120 degrees, kind of like an angle. You know, we talked about kind of go around the circle. This could be 120 degrees. Then this would also be 120 degrees as well. Okay, this is what the theorem is referring to, and this is how we mark what the measure of an arc is. It's just asking how many degrees around the circle am I going? And remember, we talked about that. About a quarter of the way is 90, half of it is 180, 3/4 is 270, and then all the way around is 360. Okay, so putting that to use here, how can we use that to solve for some different measurements here? Let's say we're given this circle here. So we're given this circle, and we see we have two chords in this circle. We have LM and PM. And it's saying, using this, I want to find the measure of arc MP. So we've seen a couple different ways that this would be used here, or we've seen this symbol before. Remember, if you're trying to describe an arc, you just put the two endpoints and then put a little curved line over it. And there's two different things that we talk about. We talked about length last time. And if it ever wants you to find the length, the actual distance, it will either say length or it will look just like this. When they want it to be an angle, which is what we see here, then they're always going to put that little cursive M, which stands for measure, and then the curved arc. So make sure you pay attention to that difference, whether it's asking for the length of it or whether you're asking for just the measure of degrees of it. And usually it'll be pretty clear because you'll either have a length or you'll have one of the measures already written out for you in terms of degrees. So let's use this now. We just talked about this theorem. We said if we have two congruent chords, which we do, they are marked for us, then the arcs across from them or outside of them are going to be congruent as well. So for instance, if this is x here, then I know the measure of arc LM is also going to be x, and we can put degrees as well. Okay, so now I have these three arcs, and we should be able to kind of figure this out or set up an equation here, because remember, we know all the angle measures around a circle are always going to add up to 360, whether that's the central angles or the measures on the outside. So I can say x plus 106 equals 360 here. Okay, so this is how I'd set up the equation. All the way around the circle is 360, and so just add all those three together. Okay, and now we have this. Now I can go ahead and simplify. So I can combine my like terms and get 2x plus 106 equals 360. And now continue to solve. Subtract 106 from both sides. These cancel. I'm left with 2x here. And then here, 360 minus 106. This is just good mental math practice. This is going to be 254. And then last step here, we know divide by 2 if I want to find x. So I get divided by 2 here, and I get x equals 254 divided by 2. Again, some good mental math practice here. That is going to be 127. And then since it is a measure, or since it is kind of an angle technically, this is going to be x equals 177 degrees. Okay, or in other words, since it was asking for the measure of angle, arc MP, since it was asking for that measure, that's 127 degrees. Okay, either answer would be acceptable here. Okay, but this is the idea. I'm just looking for congruent congruent chords, and those are always going to lead to congruent arcs, and vice versa. Okay, another thing that we can talk about here, another theorem that we can use when we're looking at chords or lines inside a circle, is what we call the chord bisector theorem. Okay, the chord bisector theorem. This one's a little bit different. It says this. It says if, it lets me write here, if a diameter, or for that matter, we'll say, or radius, because it's the same idea. If a diameter or radius is perpendicular to a chord, if I look and I see the diameter or the radius going across, and I'm told it's perpendicular to a chord, then what I can say is then it bisects the chord and the arc measure. Or let's say, well, the measure of the arc. Okay, we can write it like that. Okay, it will always bisect the chord itself and the arc that is across from it. Okay, so for example here, when I'm looking at this, let's draw a circle again. Okay, we have a center here. And let's say we have one chord. Again, we'll just try to keep it simple. We'll just keep it a straight line going left and right. Okay, it doesn't have to go through the center. And it's saying whether I had a diameter or radius. So for instance, let's say the diameter here is just starting from the bottom, goes straight through all the way across. Okay, and let's say I'm told that these are perpendicular. In other words, they intersect at a 90-degree angle. So I'll label these points here where all this is intersecting. We'll label this A, B, and C. And it's saying if this is the case, I know two things. And we'll label this as well. We'll label that D. First off, the chord itself, AC, is being bisected or cut in half. So in other words, these two segments would be congruent. So AD is going to be congruent to CD. Okay, that's one thing that I know. And then also the measures of these arcs right here are also going to be congruent as well. So the measure of what we'll call arc AB whatever angle measure or angle degree that is, it's always going to be the same as the measure of arc BC or CB, doesn't matter how you name it. Okay, so this is the idea. Okay, look for this. If I see basically a right angle, in other words, perpendicular lines inside a circle, then I know the chord is being bisected and the arc is being bisected as well. Okay, so practicing this a little bit. Example 2, let's say we're given this circle here. Okay, so we have circle R. We have all these different points where they're intersecting here, and we want to find the length of TV. Okay, well, first off, we see the idea that we just talked about. We see this chord here, and it's being intersected and is perpendicular to a radius of a diameter. Or, I'm sorry, a radius of a diameter, a radius of the circle. And notice this works with either the radius or the diameter. Either one works here. Okay, so that means that first off, these two segments are congruent here. Okay, and then it means also that this arc TU is congruent to UV, whatever those are going to end up being. Okay, and in this case, it wants us to find the length of TV. It wants us to find the length of the actual chord here. So the way that we're going to do that is we're going to look at this picture, and really we don't need even the whole thing. We just need half of it. Because if I can just find, for instance, TS, let's just write that out. If I can find what TS is, I know I can just multiply that by 2 because TS is half of it. And then SV would be the other half. So I just need to multiply that by 2 or add it to itself, whatever I end up finding for it. Okay, so how am I going to find TS here? Well, this one is a little bit tougher, but I can try to use the information that I have here. So first off, I know these two lines are perpendicular. That's also going to have to be a 90-degree angle. Okay. And so actually I can create, if we're using some things that we've talked about in the past here, I can actually create a right triangle with this. So we have a right triangle. We have 6 as one of the side lengths here, which is SR. Okay, I'll go ahead and just kind of shade that in. And then the problem is we need one of the other side lengths, and then we could use the Pythagorean theorem. So we either need one of the side lengths or one of the angle measures here. In this case, it's going to be helpful to find one of the other side lengths. And we can actually find this here. If I look at TR, I actually know what that length is because TR is still a radius of the circle. And so the radius we've already seen, we're actually given that information. The radius here from U to R is 11 if I add those two sides together, which means from T to R it's the same thing. Because remember we talked about that when we talked about the definition of a circle. They're all equidistant from the center. So if U to R is 11, then T to R is also 11 here. So now I have this right triangle, and if I need to, I could draw this to the side. Right here, I have 6, and I have 11, and then our last side length, TS, we can just call X. And so now we can use the Pythagorean theorem in order to find this here. So Pythagorean theorem, we could say x squared plus 6 squared equals 11 squared. And now I just need to start simplifying this and find out what X is. So x squared plus 6 squared is 36 equals 11 squared, we should know as well. That's 121. Continue to solve here. Subtract 36 from both sides. These cancel. And I get x squared equals, and I have 121 minus 36. Again, some good mental math practice here. This would be the square root of 70, or I'm sorry, this would be 75 to start. Okay, making sure I did that correct. 81, yep. Or actually, I'm sorry, this is going to be 85. There we go. That looks better. Okay, 85 here. All right, so now this is the case. Now, last step, we've talked about this before. I just need to take the square root of this. Take the square root of both sides. X equals square root of 85. And we've talked about this before. We would want to try to break this radical down here, but unfortunately, there are no perfect squares that are going to go into 85. So because of that, what I'm going to do is I'm just going to type this into my calculator, and I can either leave it like this or I could type it into my calculator and get the decimal. Either one would be an acceptable answer here. So in this case, let's type it into our calculator, and that's going to come out to be about 9.22, okay, roughly. Okay, so this is x, and so remember x was the side of this triangle right here, in other words, TS. So I'm going to say TS equals 9.22. And then we need to double check. Notice it's asking for TV. So like we talked about at the very beginning, essentially to find that, I just need to double TS. So in this case, we're going to say TV equals 2 times 9.2, and I could really keep that decimal in my calculator if I wanted to, and I'm gonna get TV equals roughly 18.4. Okay, so this would be about 18.4. I don't see any units that I'm given here, so I'm just gonna leave this as is. The length is just 18.4. Okay, so this is how we would set up and solve these problems here. You'll notice that the textbook really likes to tie in ideas that we've already talked about with Pythagorean theorem and trigonometry, okay? But this would be the idea. Okay, last thing that we need to talk about here. Another theorem that we can use called the congruent chords theorem. Okay, the congruent chords theorem. Okay, and we're going to say this. We're going to say in the same circle, or congruent circles, okay, either way works, whether that's in the same circle or in congruent circles, two chords are congruent. Okay, two chords are congruent if and only if they are equidistant from the center. Okay, the two chords are only going to be equidistant from each other. Are going to be congruent if and only if they're equidistant from the center. So again, for an example, what this would look like in a problem that we'd work on here. If I go ahead and draw a circle, try to draw this over here. Center, let's just draw two chords, and they don't have to necessarily be, look the exact same. So let's draw one here maybe, and then let's draw one, let's go this right here, okay? Or let's try to make it look a little more congruent. Let's go here. Okay, we're saying, or you'll see this is the case here, where we could say these two chords are congruent if their distance from here to here, which you'd have to use a perpendicular line in order to test this. And you'll see pictures like this, where you'll have perpendicular lines going to two different chords here. And we can say, if I see that these two are congruent, so for instance, we could say, you'll usually see it like this, where you'll just be given the two lengths, 2 and 2. We're saying if this is the case, then this entire chord is congruent to this entire chord. Okay, so again, another process where we're basically just going to be setting things equal to each other, and we know that two chords are the same distance or the same length. Okay, so let's practice this one, and then we'll be good to go for today. Okay, we'll look at this here. Okay, so we're saying in the given circle, AB is congruent to BC. So I'll go ahead and mark that from the start. AB, BC, those two chords right here are congruent to each other. Okay, and we're saying that is the case. DF right here is 3x minus 7. Okay, and then EF is x plus 9. And it's wanting us to find the length of EF here. So notice this is actually the reverse of what we just wrote down. Okay, in this case, we're actually told already that the chords are congruent. And this is where that if and only if piece works in. Okay, it works both ways. So if the chords are congruent, then they're equidistant from the center, and vice versa. If they're equidistant from the center, then the chords are congruent. So now that I know this, all of this is a long-winded way of saying these two chords are congruent, which means these two lines that I just marked are going to be congruent as well. So how do I set up an equation to solve for x? I can just set them equal to each other. 3x minus 7 equals x plus 9 here. And now, just simple algebra, let's solve. So subtract x from both sides. These cancel. I get 2x minus 7 equals 9. Next step, add 7 to both sides so that these cancel. I'm left with 2x here, and then 9 plus 7 is just 16. And then last step here, divide by 2, and I get x equals 8. Okay, so x equals 8, that is good here, but remember that's not what it's asking for. It's asking for the length of EF. So last step is I just need to plug that back in here. EF, we were told from the very beginning, is x plus 9, so this would be the same thing as 8 plus 9 here, or in other words, the length of EF is 17. Okay, and again, I can double check. make sure I plug that in correctly, and then make sure there's no units or anything like that, so I don't need to add that to my final answer. Okay, but this is the basic idea. A lot of things that you're going to see in this unit, or specifically in this lesson and in this homework, is just setting things equal to each other. Okay, you're usually going to have chords or different lines inside your circle that are equal to each other. Okay, so that is all the notes for today. Homework with this is 11.2, arcs and chords. And as always, if you guys have any questions, feel free to let me know. All right, thanks guys.